All right, so this is section 11.6. This is actually going to cover the last two of our series testing for convergence and divergence. This is probably my favorite section, probably because of the algebra involved in doing it. I just enjoy the algebraic part of this one. But it also is probably one of the more important of the convergence and divergence tests because of the thing that we're going to talk about first, which is this thing called absolute convergence. This actually plays a very big role in what's happening later on in the chapter. This is a lengthy section, so it will probably take at least 3 videos, maybe 4, because of the number of examples and things in here. So let's get rolling. All right. So the first thing that we are going to talk about before we actually get into the ratio test is this thing which is called absolute convergence. And the ratio test and the root test, which are the two tests we'll be covering here, are both tests for absolute convergence. Now, when I was in school, I used to think, oh, it's a test for absolute convergence. Something is absolutely convergent. Yes, it's definitely convergent. It's not really what it means. Test for absolute convergence has to do with the absolute values of the series terms. So a series, the definition here, a series which is called absolutely convergent, if the series of the absolute values of the terms is convergent. So let's take a look at what that actually means. So we actually say, okay, you've got a series which may or may not have all positive values, but then you take the absolute values of that, and if that's the case, if you take the absolute values of all the terms and you can add them up, and that's convergent, then it's called absolutely convergent. So let's look at a case here. Let's look at the series, -1 to the n minus 1 over n squared. Now we know that's an alternating series just by looking at it. If you write out the first few terms, just literally writing out the terms, let's see, if you plug in 1, that would give you a +1 on top over 1 squared. The next term, if you plug in 2, that's going to give you a -1 on top, so it's a -1 over 2 squared. Plugging in a 3 makes the top positive. And then you'll get 3 squared. Plugging in 4 makes the top negative over 4 squared, and so on. Okay, clearly that is alternating. So we can see that plus, minus, and so on. If you were to take the exact same series and take the absolute values of the terms, well, the only thing that's really going to change is that -1 to the n minus 1 on top basically becomes irrelevant. It just becomes +1 every single time. Nothing else changes. So what you would get is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so on. So that's what taking the absolute values would do. We know this second one, the absolute value one, to be a p series where p is 2, because that's 1 over n to the p power. Where the p value is 2, the n values change. So we already know, since p equals 2, that that's a convergent series. The absolute value one is a convergent series. So this is what is known as an absolutely convergent series. So we took the absolute values of the terms of the series and it converges, which means it is what is called absolutely convergent. All right, let's take a look at page 2. We also know that the original series itself, without taking the absolute values, would be convergent because of the alternating series test. I'm not going to write all the criteria out, but the series the absolute value of the terms would approach 0 as n goes to infinity, and the absolute value of the terms would decrease in value. So it would fit the alternating series test, which means it is also convergent for the original series. That being said, a series can be what is called conditionally convergent, but not absolutely convergent. Okay, what does that mean? So a series, a sub n, notice there's no absolute value there, is called conditionally convergent. And it's called conditionally convergent if it is convergent, but not absolutely convergent. In other words, the original series, as it is, converges, but if you take the absolute value, it no longer is a convergent series. That's what conditionally convergent means. So let's look at a case of that. Let's look at the alternating harmonic series. So the alternating harmonic series is -1 to the n minus 1 over n. And that one would be, let's just plug some values in here. So if we start with 1, you're going to get 1 over 1, which is 1. Plug in 2, the top is now going to be negative, so it'll be a -1 over 2. Plug in 3, the top is positive, plus 1/3. Plug in 4, it's negative, -1/4, plus, and so on. So you can clearly see that you've got the alternating series there. And we know that this alternating series is going to be convergent because it passes the two criteria. You take the absolute value, 1 over n approaches 0 as n goes to infinity, and all of the terms would be decreasing. So it does pass the alternating series test, and therefore would be convergent. However, if you were to take the absolute value of just the terms, then you would get the sum of 1 over n, because that -1 to the n minus 1 again would just become a 1 all the time. Well, the sum of 1 over n is the harmonic series, and we already know that that one is divergent. Harmonic series, also the p series where p equals 1, it's the same thing. So that would be a divergent series if you took the absolute value of the terms. So that one would actually be conditionally convergent. It converges for its original series, but it does not converge for the absolute values. That's the difference. So a conditionally convergent series converges as it stands originally, but if you were to take the absolute value, it no longer becomes a convergent series. If you take the absolute value and it still converges, then it is absolutely convergent. In other words, it converges in every way. So there's a theorem that says if a series, a sub n, is absolutely convergent, then it is convergent. It is just flat out convergent. So if you can take the absolute value of the series and it converges, then the original series is going to converge as well. The converse of that statement is not always true, as we just showed above. Okay, you cannot say that just because something is conditionally convergent, it is absolutely convergent. It does not necessarily work that way. All right, so let's take a look at a couple of tests here. The ratio test, which is probably the more useful, most common, especially again when we get into some later stuff. So the basic idea behind the ratio test is that we're trying to create a comparison with a geometric series. And if you think about why that is, which we'll talk about here when we get down to number 1, it really is identical to the criteria of the ratio test with the one small exception, and that's in number 3. So we're going to let a sub n be a series with non-zero terms. So the series is going to converge absolutely if the following criteria is true. This one right here. If the limit as n goes to infinity of the absolute value of the a sub n plus 1 term divided by the a sub n term is less than 1. If you remember the criteria for a geometric series, the absolute value of r had to be less than 1. That was the criteria for a geometric series to be convergent. Well, r is, or can be, found by taking any one term and dividing it by its previous term. So basically, this is r. Okay, that whole interior piece. So this really is exactly the same criteria as a geometric, which means that if r is greater than 1, or the a sub n plus 1 over a sub n term is greater than 1, or it says equals infinity, which of course is greater than 1, then it's going to be divergent. The only place that this is slightly different is if the limit of the absolute value of a sub n plus 1 over a sub n equals 1. If it actually equals 1, then it's inconclusive and we would have to try some other method. Okay, so this is the only place that this thing differs from a geometric series. If you remember that if it equaled 1 with a geometric series, then it was also going to be divergent. Well, here 1 is inconclusive. All right, so let's look at a couple of examples, and then by a couple, I mean a bunch. So we do have to remember some of our stuff here, and I'll just kind of put a reminder up here real quick that n factorial is defined to be n times n minus 1, n minus 2, n minus 3, and that's going to go all the way down till we get to 3 times 2 times 1. And something like n plus 1 factorial would be n plus 1 times n minus 1, all the way down to 3 times 2 times 1. Should be a times, not a minus. And you should see a similarity there, that n plus 1 factorial includes all of this, which is the same as n factorial. So you could write n plus 1 factorial as n plus 1 times n factorial. Okay, that's going to be important when it comes to simplification type stuff. So you really do need to understand the idea of a factorial. This happens a lot when we use the ratio test. Okay, so let's determine the convergence or divergence of 2 to the n over n factorial. At this point, again, you should be able to make a hypothesis by looking at this and say, okay, the top of this series consists of an exponential 2 to the n. The denominator consists of a factorial. Factorials grow much, much faster in the long run than exponentials do, which means that your denominator is going to grow so much faster than your numerator. This should approach 0 fast enough to be convergent. We just now have to show that. So let's use the ratio test, because none of the other tests are going to work. Integral tests do not work easily, especially with factorials, because it's not something you can take an antiderivative of easily. So we're not going to try an integral test. Comparisons, not easy to do on this one. All the other tests, it's not geometric, it's not a p-series. You can go through your head. We're going to go straight to the ratio test here and say that the limit as n approaches infinity of the absolute value. Now it's supposed to be the n plus 1 term, which literally means wherever there's an n, you're going to substitute in n plus 1. So 2 to the n plus 1 divided by n plus 1 factorial. Notation is going to be extremely important on this particular section. Absolute values are definitely necessary here. The parentheses, when you're plugging in n plus 1, when you have to include like a factorial after that, extremely necessary, because if you wrote n plus 1 factorial, that really means n plus 1 factorial, which is not correct. So you have to put the parentheses there. Now we have to divide this by the nth term, which is the original series. So that's what you're going to take the limit of. Now, of course, that looks like a mess. And in order to do this, we need to think about dividing the fractions is the same thing as multiplying by the reciprocal. So we're going to write this as the limit as n goes to infinity of absolute value 2 to the n plus 1 over n plus 1 factorial times the reciprocal of the denominator, which is n factorial over 2 to the n. Now, eventually, hopefully, you'll be able to skip that first step and go straight to the second step, realizing that if you have a fraction, when you divide the fractions, you're going to multiply by the reciprocal. It just saves a step. But if not, you can always just write that first step out and then do the division by multiplying by the reciprocal. Okay, another thing is we're going to reorder what's inside the absolute value. Remember that since you're multiplying fractions, you're multiplying across the top and the bottom. So it's basically the idea that if I have 2 times 3, that's the same thing as 3 times 2. So the order that you write the multiplication in doesn't matter. And really, it's like saying, okay, I've got this one fraction bar straight across the top. If you want to think about it like that, you can, because now that we've multiplied the fractions, that's exactly what you're doing. So I can put these things in any order. So I'm going to rewrite them so that I have basically like terms on top of each other. So I'll have n factorial over n plus 1 factorial, and then times 2 to the n plus 1 over 2 to the n. So now we can simplify. This is where the algebraic process comes in. So we have n factorial divided by n plus 1 factorial. Well, if you remember from what I just wrote up in the red, the n plus 1 factorial can be written as n plus 1 times n factorial. So if you think about it, this n factorial right here is going to get rid of that n factorial in the numerator, leaving just an n plus 1 in the denominator. So what we have is 1 over n plus 1 when we simplify that first fraction. And in the second fraction, 2 to the n plus 1 divided by 2 to the n. I have common bases. The base is 2. So when we divide common bases, we subtract the exponents. Well, n plus 1 minus n is just going to leave you with a 1. So really, I have times 2 to the first power, or just times 2. And now we can actually apply the limit. We can take the limit because we're not going to get some form of infinity over infinity or something like that. So now basically you have the limit as n goes to infinity of 1 over n plus 1. That, of course, goes to 0. 0 times 2 is still 0. So that limit is 0. And 0 is definitely a number which is less than 1. And because what we just got for our limit is less than 1, this series is convergent. All right, let's try one more example, then we'll come back with a second video and do a bunch more examples, and then that'll lead us into what's called the root test. All right, so determine the convergence or divergence of that series right there. Okay, that's kind of messy. We've got a polynomial times an exponential divided by some other kind of an exponential with a different base in the denominator. So this is a messy one. The ratio test is definitely a go-to here. So let's take the limit as n goes to infinity of absolute value of the n plus 1 term, which will be n plus 1 squared times 2 to the n plus 1 over 3 to the n plus 1. And then remember, what we're going to multiply by is the reciprocal of the original, which is 3 to the n over n squared times 2 to the n plus 1. And now it's time to simplify. So again, the idea might be, let's reorder everything, and eventually maybe you'll be able to skip this part too and just kind of see what's going to simplify and how it's going to simplify. But let's reorder. So we're going to put things into, in this case, I've really got 3 different pieces. I've got that polynomial on top. I've got an exponential with a base of 2, exponential with a base of 3. So I'm going to reorder. Let's start with the polynomial part first. N plus 1 squared, and then the polynomial in the denominator is n squared. Okay, so those are together. I'll reorder, so I've got a 2 to the n plus 2 on top, and I've got a 2 to the n plus 1 in the denominator. And then my last one, I've got a 3 to the n on top and a 3 to the n plus 1 in the denominator. That actually look like a 3 and not a B. There we go. All right, the n plus 1 quantity squared over n squared, you can't really simplify that one. The 2 to the n plus 2 over 2 to the n plus 1, again, subtracting the exponents. The n's are going to subtract out, and then 2 minus 1 is going to give you 1. So we're going to get a limit as n goes to infinity. The absolute value of n plus 1 squared over n squared. Again, that didn't change. And then the 2 to the n plus 2 over 2 to the n plus 1 is going to just leave you with a 2 to the first power. And then 3 to the n over 3 to the n plus 1, will if you subtract the exponents, you'll get 3 to the negative 1. 3 to the negative 1 is the same thing as 3 in the denominator to the first power, so that becomes over 3. So now if we were to evaluate the limit, technically that 2/3, which is a constant, can come all the way out to the front. No reason to really remove it here, but we could. The limit of the n plus 1 squared over n squared, the highest power on the top and the bottom, if you were to distribute everything out, would be n squared. And so the leading coefficients of that would be 1 over 1. Don't forget you've got to multiply it by that 2/3, which is going to give you a limit of 2/3. And again, 2/3 is definitely less than 1, and therefore this series would be convergent. All right, plenty enough for the first video. Let's stop this. We'll come back with some more examples.